Karen, Josh, and Jen, thank you so much for taking the time to join us this evening. Jen Walton is our moderator, and she has spent 2 decades crafting strategic communications and public relations strategies and programs for technical, scientific, and climate change focused agencies, NGOs, excuse me, and nonprofits. Her special expertise lies at the nexus of communication, environmental change, and extreme weather and crisis response. Necessary capabilities to help organizations prepare for and respond to the true nature of the issues we face today. She now runs her own communications consulting firm where she advises executives and managers around strategic planning, change management, crisis communication, and leadership and internal communication. She is a storm chaser and founder of the Girls Who Chase initiative, which empowers and equips girls and women to pursue storms and the science. Jen, it's all you now.
Well, thanks for joining us, everyone. Clearly, this is a topic of high interest right now, and tornadoes are on everyone's mind due to twisters coming out this last weekend. So it's been a really exciting few months for us in the storm chasing and tornado science space. So I'm excited to introduce Karen and Josh. And I'm going to read 2 more long bios, so stick with us here because these 2 have some pretty impressive backgrounds. Karen Kasiba is the managing director of the Flexible Array of Radars and Mesonettes, or FARM facility, and research scientist at the University of Illinois. She has a Bachelor of Science in Physics, and Master of Science in Physics, and as well as a Master's in Teaching Education, and a PhD in Atmospheric Science from Purdue. Her research mainly focuses on the kinematics and dynamics of severe convective storms, characterizing the low-level wind structure in tornadoes, and understanding the boundary layer winds and small-scale structures in landfalling hurricanes. Key to her research is executing field projects to collect data that can be analyzed to better understand and predict these hazardous weather events. Additionally, she's passionate about science education, regularly participating in outreach activities at schools, museums, and festivals, and online and through media interviews and consultations. She's a strong believer in experiencing weather from the inside of a mobile weather radar, and has participated as a radar operator, project scientist, and project leader in a multitude of field projects, including those studying tornadoes, hurricanes, snow, convective initiation fires, and nocturnal convection. Dr. Josh Warman is an atmospheric scientist and inventor of the Doppler on wheels, of which you see one behind them, a mobile radar system designed to get close to some of the most dangerous weather on Earth in order to obtain high-resolution, detailed data that has revolutionized our understanding of tornadoes, hurricanes, wildfires, and blizzards. He founded the nonprofit Center for Severe Weather Research, and he has led multiple large multi-agency deployments to study severe weather, including serving as the principal investigator of the Vortex 2 project, the largest tornado research project in history. He now serves as the executive director of the FARM facility in partnership with the University of Illinois, which comprises multiple DOWs and other types of mobile radars, mobile mesonettes, and deployable tornado and hurricane pods, and other sensor equipment. Dr. Warman's research includes tornado climatology, the process of tornado genesis, hurricane behavior, and bistatic radar. Prior to founding the Center for Severe Weather Research, he was an affiliate scientist at NCAR, working on bistatic radar, and an associate professor of meteorology at OU. He has a Bachelor of Science in Physics and Interdisciplinary Science, a Master of Science in Meteorology, and a scientific doctorate in meteorology, all from MIT. So I am now going to hand it over to Josh and Karen, and I'll just reiterate what Gideon said in his introduction. We will not be monitoring the chat. We will be taking questions from you all through the Q&A button at the bottom of your Zoom screen. So if you have a question for Josh and Karen, either about their presentation or something you would like us to process through to them, that is the place to do that. So I'll be watching questions during their presentation, which is going to be about 15 to 20 minutes. And then we'll start with the Q&A because we know you guys have a lot of questions for them. So I'm going to go ahead and hand it over now if you all want to go ahead and share your screen and get going.
Okay, this will take a sec.
Now you get to see the top of Josh's head.
And nose.
An extra bonus that
There we
nobody
go.
was
Oh,
anticipating.
and that's the last slide. Ah. Well, I clicked on the first one. Hold on. All right, this
Not
came up.
about tornadoes, not so much about PowerPoint.
I literally clicked on the first one to start this. You saw that.
Yes.
Okay. We're going to do that again. I'm on the first one. I'm just going to go to the first one and then share.
We're better.
I would hope so. There we go. Okay.
Actually.
Everything. So we have no idea what the background of people are who are attending. So we're going to try to do some introduction of the basics. If you've never heard of what a tornado is, this isn't going to help. But we just start with some introduction about why we're out here and what we're using. So we start with scientific questions. We're not out, different than chasers, we're not out here for fun or selfies. In fact, somebody was saying we have no selfies of ourselves in tornadoes. We're basically focusing on questions we have about tornadoes and questions that the community has about tornadoes, which are important. First of all, which supercells are going to make tornadoes? There's a lot of supercells there. Most of them don't make tornadoes. We sort of know that. Even the supercells that do make tornadoes, when are they going to make tornadoes during their lifespan? These are really hard questions, and we don't have good answers for that. That's why false alarm rates for tornado warnings are so large. Once a tornado forms, how strong is it going to be? There are 1,000 or more tornadoes across the United States every year. Most of them are not so strong. Some of them are extremely powerful. Those are the ones which are most hazardous. And we don't really have good skill at forecasting which ones are going to get strong. We sort of know which days might make stronger tornadoes, but even on those big outbreak days, most of the tornadoes aren't so strong. There are a few strong ones and most of them are weak. Is there any ability to learn which ones are going to be which? Similar to that question, which ones are going to be long track tornadoes, which have the capability of causing much more damage, the potential of much more damage, and which ones are going to be very short? Again, even on an outbreak day, there's a lot of very short-lived, weak tornadoes and a few that are very significant. How strong are the winds at the surface? Well, that's probably the most important, impactful characteristic of a tornado is how strong are those winds, and we just don't know. We've been taking measurements with the DOWs. We try to infer the damage, try to infer the wind speeds from damage, but fundamentally, there are big questions about that. And again, all of these get back to the questions of how much damage is going to occur from particular tornadoes. In order to answer those questions, we can do conceptual models, we can do computer models, but really to dig at those questions, to verify that those computer models and conceptual models are correct, we need to have accurate characterization, a big word for measurements of what's happening in the near tornado environment and the tornado winds themselves. So
Hey,
how do we do that? Yes?
Hey, Josh, if you're sharing a presentation, we're not seeing it.
Oh, so we have to, sorry. Do we not do a
Yes.
Ha!
Ooh,
Oh, nice.
excellent.
That's just excellent. Okay, excellent. We were sharing a presentation,
It was
but,
really exciting.
but we never hit
It was for
the,
both of you, which is fantastic.
Share
yeah,
screen.
actually, it was really good.
Yay.
It's okay. The first slide was just words. Yeah, it's this screen. Hold on.
Yay.
We are.
Now we're seeing a screen share.
Yeah, the first one really was just text. So, but now why is that not? There we go. Okay. Are you seeing something now?
Yes.
Oh, looks good now. Yep.
Thank you.
Excellent. I can show you the previous slide. It was just text. There you go. Now at least it's recorded. Now, so how do we measure those? Again, maybe a lot of people know this already, but we go out with mobile radars. There's one on the left with a tornado on the back during Vortex 2. We have mobile mesonets, which are really just weather stations on wheels, no rocket science there. And we try to get them back and forth in front and around the tornado so we can measure that environment. And then we have tornado pods. There's one being dropped in front of a tornado. Tornado is pretty far away in that picture, but one being dropped in front of tornadoes. Those are just rugged weather stations, nothing real special about them. And then we try to launch weather balloons of different varieties. near the tornadoes. This year, we've been trying to get them into the tornado and failing, but we're trying to get them in the tornado. So what do we see with a Doppler on wheels? On the top left is a picture of a supercell from a stationary radar about 40 kilometers, about 30 miles away from that radar. And in that, it's great. You see a hook echo. You can see a little orange pixel right where the tornado is occurring. With modern radars, particularly if they're close enough, you can see these tornado debris signatures, and you can get an idea that a tornado might be happening, but you don't know much about that tornado. If there's a debris signature, maybe you know it's strong enough to loft debris, but it's really hard to know whether it's a large tornado, how strong the tornado is, whether it's getting stronger or weaker. The radars are just too far away, and they're sampling too slowly every 5 minutes. So that's about the lifespan of a tornado. If we get closer to the tornado, we see lots more detail, and there is just not even our best image of what it looks like close up to a hook echo like that, where we're seeing a clear eye in the center of the tornado. We're seeing the winds going towards or away from us, which are the signature of a tornado. Again, you can have a whole course in that, but that's roughly what we're seeing. So looking up closer, you see a lot more detail. That's all there is. The DOW see thousands of times more detail than stationary tornadoes. We see a lot of complex structures. In fact, most tornadoes we're seeing have pretty complex structures. Here's a particularly complex and, sort of ugly one where there's the hook echo there, but inside it, there's a whole bunch of little teeny eyes, and there's subvortices. In fact, some of these subvortices had subvortices within them. So it was a very complex structure on this particular night in Kansas. Not a famous tornado, but just one that was very, very complex. If we can observe the tornado for a long time, we can watch its evolution. This is a too often shown loop of the Goshen County, Wyoming tornado from way back in Vortex 2, where we watch the pre-tornadic, tornadic, and weakening phase of that particular tornado. With our rapid scan radar, which has multiple beams, so every 7 seconds we get a volume in that tornado, we can watch the fluid motion of that tornado much better. We can watch this debris ring form and to see that with much finer temporal detail. Just rushing through these because, again, this takes a long time.
My turn.
Karen goes now. Yes.
All right, sorry, we're doing this handoff here. So what do we learn, and what are we trying to see with these different observations? If you have more than one radar out, you could do something called dual Doppler analysis. So you could look at the tornado from different perspectives and reconstruct a three-dimensional wind field. So you could look at updrafts, downdrafts, you could look at vertical vorticity, horizontal vorticity. And if you have enough of this type of data, you can go backwards in time and look at trajectories. So you could look at the path of the parcels that go into the tornado. In this case, it's showing parcels coming in from the forward flank and also the rear flank downdraft of the Goshen County tornado. Additionally, if you have thermodynamic measurements out there, these pod measurements, the surface thermodynamics from mesonets or pods, and if you have soundings, you could say something about the air surrounding the tornado. You could say how buoyant it is, how warm it is, how cold it is, how moist it is, and how does that affect tornado intensity. And if you have soundings, you could also say something about the origins of that air, where that air actually came from that makes up the tornado. So
We get to click in it.
Okay. So a quick example of not having two radars out there, because that happens a lot too. So a lot of times we're deploying these pods, we're trying to get the low level winds in these tornadoes, trying to measure the winds very near the surface. But what happens, as you could see in this loop from McCook a few years back, is that the tornado forms. It's a very complex evolution, a very unsteady evolution. We see that a lot in tornado genesis, where it's not all of a sudden, boom, you have a tornado. There's a lot of things that are going on before the tornado actually forms and becomes mature. But those purple things there, those are the pods, those purple dots. And if you look, you can see that the tornado goes right in between them. So we don't get wind observations in the tornado. But what we do get is we get thermodynamic observations around the tornado. So we see what the air is like surrounding the tornado.
Yes.
Yes. And then you can make plots that look something like this. This isn't the greatest plot, but like I said, you could look at the origins of the air, but you could also look at the buoyancy of the air, more buoyant or less buoyant air is coming in, and how that affects tornado evolution. So all those lines that you see there, probably not very well. Those are just contours of different thermodynamic variables. And you can see that different air masses are making it into the tornado. And in particular, there's a warmer air mass near the tornado, and it looks like buoyant air from the surface is making it in. So that's some of the old stuff that we've collected. What we're going to talk about now and what we're going to talk about next is what you guys probably are all here for, is to talk about the BEST project. So the boundary layer evolution and structure of tornado study. Took a lot of work to come up with that one, which is our tornado genesis and tornado wind structure project that we did last year and in earnest this year. Fine, don't do it for me. So the BEST project, and you're totally next after this. get itchy. So the best project really is taking out different radars, but trying to get very, very close to the tornado. So not backing up a lot, but getting in there, getting a few kilometers from the tornado with 2 radars. So again, like I said, with 2 radars, you can reconstruct the 3-dimensional wind fields. You can see updrafts and downdrafts around the tornado. We also are taking out our tornado pods. Tornado pods, once again, are trying to get wind observations in the tornado, but also can get you thermodynamic observations near the surface. And then last but not least, we took out swarm sensors. So basically, instead of doing weather balloons that go vertically upward, these weather balloons are neutrally buoyant. And the idea there is that these weather balloons will circle into the tornado and map out the thermodynamics as it circles into the tornado. So then we have this very high density data set, these 2 radars, fast observations every 7 seconds through the tornado, 3-dimensional winds, pods, and thermodynamics surrounding the tornado. So for best, we drove a lot. So 2004 was our big year, and you probably saw a lot of stuff on Twitter about the different tornadoes that we intercepted. But really, we only observed tornadoes on a few days. But at least 2 of those tornadoes had winds of over 100 meters per second. And I think it's here.
All right. So we'll talk about a couple of those cases. One was in southern Oklahoma. I think most people call this the Duke tornado. And our deployment was pretty much like the diagram Karen just showed. We had 2 radars that were deployed near this town called Illustre. They weren't too far apart. That blue area is our dual Doppler area. That's where we can get those vectors, which are necessary for calculating trajectories, updrafts and downdrafts. And we deployed ahead of this tornado area, which looked like it would make a tornado soon. And it was coming right at us, so we felt really smart. We sent out teams with balloons and pods to that black star there, right in the middle of our area. And we'll go back to the beginning of that loop again. You'll see looks like it's heading right towards us. Those the purple arrows are showing where we think the tornado might go. Now, we can't really predict exactly where it's going to go, but it looked like the whole storm and the tornado might be coming towards us. So we felt really smart. This looked just like our diagram. The problem is, well, there were 2 problems. One, the tornado didn't really cooperate. And if you look, it gets into our study area and then it takes a sharp left turn, just avoids us. So we did get a lot of great radar data, but we didn't get data with our pods or get balloons into it. Now, there was a second reason we didn't, and it's because both our pod team and our balloon team went down dirt roads and got stuck in the mud. But we were still hoping they could somehow get some data near them, or even if the tornado came really close, they get data.
There was balloons from another team.
But there was another team from Penn State that was launching balloons. And they were launching swarms, and they were trying to study hail, really, and probably didn't succeed too well here getting hail data. But they launched some balloons into the environment of the tornado. So we think this will be some very valuable data combined with our radar data. So that's pretty exciting. Since we had 2 radars there, we were able to do dual Doppler, and we were able to do it every 7 seconds. So we're looking at very rapid update dual Doppler. And this is what that tornado looks like with different dual Doppler fields. So on the left are the arrows, the wind vectors, and we're contouring in blue contours the vorticity in that tornado. And then in the shades there is the wind speeds. And we're seeing a lot of variation. We think we could see some subtornadic scale features spinning around that tornado. This is very hot off the press kind of stuff, so we've hardly analyzed it at all. On the right, we're looking at updrafts and downdrafts. And we can see that there are some updrafts in the forward flank. There's an updraft wrapping around into the tornado. There's downdraft coming around with the RFD. But there's a lot of second-to-second variation. And we have some transects because of the balloons and also because of our stuck vehicle there, the mobile mesonet. We still got some transect through the environment. Even when we fail, we can still get some environmental data. So we're pretty excited by that. And then we might transfer to you. No. Yes. Oh, okay. So the next tornado, well, you have to tell me when we switch. So, sorry, we're tag teaming a lot. The next interesting day, there were several days actually that were interesting, but we're focusing on 2 of them here, was the Greenfield, Iowa day. The famous tornado was the one that went through Greenfield and killed people, caused a lot of damage. There were several tornadoes that day. Here's a map of just some of them that we were sampling with the Dows. There's 2 small ones there on the left. There's the long track tornado that went through all the wind farms, wind turbine farms. Went through Greenfield and actually made a second tornado right near Greenfield that formed over the Dow, that red line there, or those red dots. And this is a loop showing what it looked like when it went through Greenfield. In fact, the tornado was dying as it went through Greenfield, but it was dying and very intense. We still don't know if it was getting stronger, but it was still maintained a very strong tornado as it went through the southeast part of town. And as you can see, a second tornado forms and leaves the tornado as it goes. So it should be there within about a 2-minute period. If you were in that northeast or Greenfield area, you would have had 2 very strong tornadoes pass over you within about 2 minutes. You probably would not have known what's going on. But we measured very, very strong winds in that tornado. We had Doppler winds, just the raw Doppler over 270 or around 270 miles an hour. And the peak ground altitude winds were calculating about 310 miles an hour. Part of that is because it was a very fast moving tornado, about 45 miles per hour. Fortunately, very, very small, really just covered a couple blocks with the very damaging winds. Most of the town of Greenfield had much weaker winds. And that was it. Okay, so we're mapping out, basically we can map out the size of the tornado, which you can see that's basically the radius of maximum winds. And you can see it shrinking as it goes through Greenfield, that tornado. And we don't even have the second tornado listed yet on this plot. The DOW is the rightmost star there. And on the left, that left star is a pod, which Jan and her team dropped close to the tornado, but we were hoping to get it into the core flow, but it was very small and wasn't really moving the way we thought it would move. Still me. Damage pictures, also some transects of thermodynamic data. Even though we didn't get it in the tornado, we sampled a lot of the air that was going into it. And in many ways, that's much more important for understanding why the tornado got strong or lasted, or why it was dying. Why was it contracting when it dies? Sometimes tornadoes get broader and weaker and they just dissipate. This one maintained a very powerful, perhaps even an intensifying intensity as it died. Now, yeah.
Okay, so what are we hoping to learn, and what are some of our outstanding questions with this data? So one of the things, as we've mentioned, is looking at the winds near the surface, the winds that are doing damage. So we know somewhere, aloft, there's some high wind speeds, and we know at the surface there's 0. But what's really happening between what we see 100, 200 meters above ground level, and then what's happening at house level? So we're trying to really ascertain what those structures are. A lot of the information, a lot of the data that we have and that we've been looking at is usually from open exposure in fields, not in towns. So there's no reason to believe that even though we think winds are stronger near the surface, that they might be in this situation just because there's houses and other structures that might also impact the wind speeds. So the winds may be blocked below this 50 or 60 meters above ground level. This seems out of order.
It wasn't.
Yeah. Okay. Yeah. Sorry. That's why I was like, wait, what's going on? Because we did do a study that was what I was sort of talking about, where we looked at numerous tornadoes where we had wind observations below 100 meters. So again, trying to ascertain what the winds are near the surface. And in general, with the cases that we had, we found that winds were about 31% stronger at 15 meters than they were at 100 or 140 meters above ground level. And 100, 140 meters above ground level, those are usually the levels that mobile radars are out there measuring. So again, we really want to know what's happening under that level, what's happening near the surface. And we want to know what's happening near the surface in a variety of different exposures and different wind regimes. So last but not least, and we'll probably be ending with this and talking about this soon, in terms of EF rating, certainly everybody's talking about Greenfield tornado and an EF4 rating. But another study that we did looking at, again, a whole bunch of tornadoes, the tornadoes are usually stronger than suggested by the damage survey. And of course, that's not really surprising because there needs to be structures to be damaged in order to get those ratings. So in the case of Greenfield, even though we're seeing winds of 270 peak Doppler, 310 ground relative, that doesn't necessarily mean you're going to get an EF5 rated tornado. You need EF5 rated structures to do that type of damage. Oh, that's sort of the same thing.
It's sort of the same, just on the average.
Yeah.
Yeah.
Yeah. Go ahead.
Yeah. What we found on average, the ratings, the tornado damage ratings from the EF scale are about a category and a half low. There's a lot of spread. If they go through towns, sometimes they're better. But if they go through open areas, they can be 4 categories low because we've measured very strong winds up near 200 miles an hour in tornadoes going through fields, and they get rated EF0, EF1.
So even like El Reno, EF2.
Or EF3.
Yeah.
El Reno is EF3, and we're measuring, in some multiple vortices, some very strong winds. So it's not, sometimes they agree, but often, in fact, on the average, the EF ratings are less than what we measure with the DOWs. Again, not surprising that would be the case. And that is it.
Right, because we're thinking about hurricanes.
Yeah, I know Jen said everybody's thinking about hurricanes now, but,
Everybody's thinking about tornadoes.
but we're not. We're thinking about hurricanes. It's hurricane season soon and fire season soon. So
Well, fire season, I think, has already started.
already
It's
started
definitely
smoking
already
here.
fire season. Yeah, at least for those of us getting smoked down here. Yeah.
Feel free to ask us questions about hurricanes and wildfires
In addition to tornado.
in addition to tornado.
Yeah. What are you pointing
We're
at
done.
in that photo, Josh?
I think there's a fire over there. I know
Huh.
that because I'm an expert.
Excellent. All right. If you guys want to pull down the presentation so we have a bigger view of you all, that would be great. And I've got a fantastic list of questions here. Thank you, everyone. I've kind of organized them into different topics. And we had a few that were sort of aligned with one another. So let's start with, there's a lot that we had several questions about tornado genesis. And a couple of them are the like violent tornado questions. So I'm going to start with the funnest one, in my opinion. What is the closest you guys have been to a violent tornado?
Euro, unfortunately.
Was Gary?
Yeah,
Yeah.
so.
You were in a tornado,
So
Gary, though.
we have sampled
Yeah.
probably 250 or so tornadoes with the DOWs, mapped out the winds in about 250 tornadoes. We've been hit a few times over 25 years. We're not trying to. I think in Geary, arguably, we were inside, depending on how you defining the edge of a tornado is pretty tough. Even in some cases, defining the radius of maximum winds, the way we are more strictly defining a tornado, is difficult. But
Well, defining it at MPS. I mean,
Yeah.
that's scary. Yeah.
Yeah. So way back in 2004, in central Oklahoma, there was a tornado in near Geary, Oklahoma, that made winds around 200 miles an hour, very strong. I think it was EF rated at 2 or 3, but we were measuring winds 80 some meters per second. So very strong. And we kind of got caught in it because it was so large. So it was kind of surprising we were in there. The Greenfield tornado, we were 800 meters from the center of that tornado, and I think about 300 meters from the edge of the damage, roughly. I don't know what really is counted as the edge of damage,
Yeah.
but roughly speaking. So we were close, but to the side of that one.
Got it. And for those of you, sorry about this, for those of you who joined us while Josh and Karen were presenting, we're taking questions through the Q&A button at the bottom of your Zoom interface or wherever it is on your Zoom interface. The chat is not being monitored, and raising your hand won't do much for you in this case. So if you've got a question for Josh and Karen, send it through the Q&A and we will drop it into the queue here. Another tornado question. Sorry, we're talking tornadoes today, guys. If there are multiple tornadoes going on at the same time in the same general region, how do you decide which one to intercept?
I mean, Greenfield, it became obvious that that was the one to intercept. Yeah, I mean, that's a tricky question. I mean, sometimes it becomes obvious which one's going to be sort of the dominant or the stronger tornado. I mean, I should say in Greenfield, we were driving around a lot trying to decide. So we'd stop, we'd deploy, we'd scan a tornado, we'd say no, we'd move north, we'd do that again. So there's a lot of that where we're sort of deciding what to do. But I think after a while, the Greenfield one became sort of the more persistent circulation. So we went after that.
I mean, sometimes it's logistics. So let's say there's a tornado ongoing, but it's ahead of us and moving away. It might take a while to catch up to it, and there might be another storm that's coming our direction. So we're just sort of playing the odds that we have more of a chance of getting our system set up the way we want to in front of something that's coming our way. So our scientific objectives are much more complex than somebody who might be looking at those tornadoes recreationally, where if you get close, if you get a good picture or selfie, that's a success. For us, that's not a success. That's a failed day. What we really need to do is get multiple radars and get instruments in the right places. I mean, Jen, you might remember, everybody's going, yay, yay, we got great data in the Duke tornado. And I'm thinking, we didn't get everything in the right place. So there's a lot of glass half empty, half full situations for us. And what we're trying to do is get the fullest glass we can, which means sometimes maybe chasing a weaker tornado or something that's not making a tornado in order to have a better chance of getting all of our pawns in the right place to get the scientific data we want.
I mean, sometimes obviously we've been burned chasing the wrong tornado, wrong storm.
Like anybody,
yeah.
Sure. I mean, there could be 3 or 4 storms going and we choose the wrong one. I mean,
or we choose the one that's up and coming.
And it doesn't.
Yeah, and it doesn't.
Yeah. Sure. Yeah, there've been notable days where hey, we're not going to be suckered on that storm. We're going to wait for this next one because it's in a better environment, and then nothing happens, right?
Yeah.
It was we still suffer the pains of those days.
Yeah. And it's equally frustrating, of course, to look at like the path of Greenfield and say, yeah, we didn't get the pod directly in the path while we were as close as we were, right? So this stuff is hard.
The Greenfield Day, I mean, we set out in the morning already knowing that we were not going to achieve all the objectives in those diagrams like we showed with Duke. Duke was a day where tornadoes were probably going to be moving slowly. We were in some fairly open territory in southwestern Oklahoma. We had a lot going for us logistically. Greenfield, we knew everything was going to be super fast moving. We were in an area of the country in Iowa where it's also challenging. There's lots of trees and towns and things like that. So we already knew we'd only accomplished some of our objectives there. But the speed of those storms meant it was going to be very difficult to know for sure that we could drop our pods and get things in the right position. I think we were a combination of skill and adaptability and lots of luck that we were able to get the data that we did.
And we actually changed our plan. I mean, that wasn't actually our plan for the day. Our plan for the day was going to be to flop down and wait for the storms to come to us, and not do what we did where we, drop south, drop north, drop east, drop west. So we almost immediately broke what we had set out to do that morning. Like gas station.
Yeah. In big projects, I mean, you were talking about going back to Vortex 2. We actually had different playbooks basically for slow days and for fast days. And really on the one day that had storms moving as fast as the Greenfield day, we did an entirely different experimental design where we just cast a net in front of the storms and waited for things to pass through us instead of trying to chase them, because it's almost impossible to scientifically chase storms that are going this fast. You can chase them recreationally and maybe get some pictures or get close to one. But in terms of getting several instruments in the right place at the right time with storms moving this fast, you pretty much have to get out in front to get the data. We were lucky that we were in essentially a chasing mode and got as much as we did.
Since we're on Greenfield, I'm going to shift to Greenfield. One of the questions I feel like we've actually gotten several times and was repeated today is, when did you record the over 300 mile an hour instances of wind speeds? Was it when the tornado was in town, before town, consistently throughout?
I don't have the second in my head, but it was in town.
Yeah.
Definitely it was in town. Yeah. We didn't have, so with the radar that was close up, we didn't have a lot of data before town.
Yeah.
We got set up and then a minute or two later it went through town. We were very last minute driving through the town and getting set up.
I mean, there were several high wind speed sweeps through the tornado. I mean, obviously that's the highest, but it wasn't, a peak and, low wind speed surrounding it. It was pretty high for several of the scans.
Yeah, but it went through town very fast.
Yeah.
I mean, probably less than, it's going 45 miles an hour. I mean, how long does it take to go through a little town like that? So less than a minute. But while it was in town, definitely.
This is interesting. So was there anything in the data, at least so far, that you found particularly surprising from Greenfield?
I was surprised that a tornado formed over our radar and then went northeast. We were not expecting that. That's not in our experimental design.
Didn't see that one coming.
Well, we didn't, because it sort of, we were focusing, the problem is, we're looking at the squirrel, and this other tornado came right up over it. So that was surprising to us, unpleasantly. Basically, as we're watching the Greenfield, as we're watching it come into town with the radar, it got really windy at the Dow, and we didn't know why. I didn't know why.
But we knew it wasn't the Greenfield tornado.
We knew it wasn't the tornado. In fact,
Yeah.
So I'm in the front and noticing it's getting really windy, and I'm looking out the window and not really seeing much. And Karen's in the back looking at the radar, and I'm probably double and triple and quadruple checking that that's not what we're getting hit by. And it clearly wasn't. It was still half a mile or 3/4 of a mile away from us. So that was surprising.
I was surprised how small it was. I mean, the whole time we were tracking the tornado, I mean, how small it was and how strong it was. I was very, I'm not actually paying attention to how strong it was, because it was such a quick deployment for us. So really just focused on the tornado, but it was just so tiny in terms of zooming in and looking at it and tracking it. I was very just shocked at what a compact tornado structure it was. And then when we actually saw what the wind speeds were after the fact, I was like, whoa.
Yeah, we knew it was strong. In real time, the difference between 200 miles an hour and 300 miles an hour, we're probably not noticing that too much in the radar. It's one of those bright colors. But yeah, what Karen's saying, the size of this. So a typical tornado, the way we define the diameter of a tornado is not from damage, because that's quite variable. But we're trying to define it in a kinematic way, which is the sort of the rough circle, the diameter of an approximate circle that's enclosing the maximum winds. The maximum rotational winds. That's kinematically kind of a repeatable measurement. And on the average, we see tornadoes are 300, 400 meters across, so about 1,000 feet across. This tornado was about 1/3 that size when it went through the center in Greenfield. It was more average to the southwest. It was a larger tornado to the southwest, but as it was in its final minutes of life, as it went through Greenfield, it contracted considerably. And we don't know why. That would be very interesting to know. Hopefully some of our thermodynamic measurements with the pod and with the DOW and with the mesonet that were there will shed some clues on that. But we don't know yet. This is still pretty fresh data.
And just to clarify too, because we have a question about this, the yellow things on the ground behind you in front of the DOW are indeed pods. So folks, when we're talking about pods, that's what you're seeing.
Oh, yeah.
Yeah. So thank you for that question. So interesting comparison question. How, and this may be a little bit too much detail for this conversation. How favorable would you say were the conditions for something like Greenfield compared to the conditions for the 2011 super outbreak?
We knew it was going to be a big day.
I mean, first of all, in retrospect, I don't know, not as favorable for as many tornadoes, right? Because we know not as many formed. But leading up to it, we knew there was a potential for powerful tornadoes and probably multiple tornadoes. I don't really have them side by side in my memory looking at them. I mean, it's possible there was a broader area of, I'll say juicier conditions, not to be real scientific about it, for that kind of outbreak than this one. So it might have been a smaller area. How many tornadoes were there? I don't know the count even of how many there were on Greenfield Day. Obviously, at least several, maybe dozens. I don't know the numbers.
In 2011, didn't they have two?
Oh, 2 rounds of tornadoes? Yeah, there might have been.
Yeah.
We're not great tornado historians, so.
Fair. Oh, these are such great questions. I'm going to probably do one more Greenfield, and then we're going to, we've got a lot of questions on tornado genesis. And thank you all. These are such fantastic questions. Thank you so much for being so engaged in this topic. actually, you know what? I'm going to shift away from Greenfield and to tornado genesis. So a lot of the questions center around the mechanism of formation itself. So which thing have you found to be the most important in tornado genesis to date? Elements such as terrain, RFD, right? I'm going to say rear flank downdraft for folks who may not be familiar with the acronyms, forward flank downdraft, or even smaller scale dynamic features such as streamwise vorticity, cold pools, et cetera. Is there something that stands out for you that has kind of led for like in a pattern that you've noticed, or is it really just case dependent? It's a big question.
Oh, that's a big question.
Yeah.
Look, so if we knew the answer, and if there was a single answer to that, you know, we would have written a paper called "Tornado Genesis Solved," and you know, it would be. And we would have written that paper.
Yeah.
So since that paper is not out there, we still don't really know the precise answers to that. So Karen was talking about how we've seen a lot of unsteady processes happening where it looks like there's surges or bursts of activity that's going on. And we've seen changes with multiple either surges or multiple RFD surges or enhancements happening. There's been discussion a lot about what the temperatures and buoyancies are in those RFDs, because some of them may be colder or warmer than others. And do we have essentially Goldilocks problems where you need it cool enough, but not too cool, buoyant enough, but not too buoyant? There have been certainly streamwise vorticity and those things factor into these, right? Because at some point you want to tilt and stretch that. But the mechanisms of how that happens, the details of how that happens, and why does it happen when it happens? You know, why are, you know, you have a lot of these supercells. Why are some of them doing it and most of them aren't? And why are they doing it when they do it? And again, why does that result in stronger or weaker tornadoes? We just don't know. And so there have been papers about other subtleties involved with this, like these vorticity rivers, or there's a recent paper out about.
Yeah,
other terms.
Right? Yeah, I mean, there's certainly, I mean, you sort of hit on all the theories out there. And a lot of these theories come from numerical modeling, because it's not easier, but I mean, you could run sort of controlled simulations and numerical modeling. The tricky thing obviously is, I mean, they're both tricky, but getting the observations to look at these theories, to look at these ideas, either to prove or disprove them is the hard part. So as Josh mentioned, I mean, downdrafts, buoyancy, friction is being looked at, sort of pre-existing vorticity piling together, and coming together to make a tornado. There's a lot of stuff out there.
Sure.
And like I said, a lot of it comes from numerical modeling. Some of it comes from observations.
These little beads of vorticity.
Yeah, that's what I meant by piles.
Yeah.
Vorticity piles.
Is it a river? Is it beads? There's a lot of theories out there, really. If we knew the answer, if there were one answer, you'd see a paper called Tornado Genesis Solved. So it's possible that it's a combination of different ones. It's possible there's some subtleties we haven't measured yet. I mean, terrain, people look kind of at terrain, but you know, you get tornadoes in hilly, semi-forested terrain, like in the Southeast or in Iowa, and you also get them in the flattest possible parts of Kansas. So we know they can occur in different situations. It's possible that there are different ways tornadoes can form, and that's unfortunate. Scientists hate that. You know, if there's 4 different ways it could form, it just makes it much more complex. One of the real limitations of our observational studies of the real world atmospheric studies is that we don't have that repeatability. In a computer model, you have all these knobs and you can turn as many knobs as you want. And, you know, you can turn knob 1 and see what happens. You can turn knob 2 that happens, and you can have storms that differ just in one characteristic. So you can run a simulation and then you can change the cape by 10% up or down. You can run a simulation and put a hill in it or take the hill away. You can run a simulation and put another storm there. There's things you can do in a computer that happen in the real world, but you don't have control over them. So the Greenfield tornado happens and it's strong. Well, another tornado happened that wasn't as strong, but there were 20 different things that were different about that environment. than about the Greenfield one. And what was the important factor there? We don't know. So we do these case studies, and I'm sure we will do a case study of that Duke tornado because it's a valuable data set. We have all this dual Doppler, we have some thermodynamic. We'll analyze that tornado and we'll say, hey, look at this feature here. There was a RFD surge, or there was a vorticity blob or river, or it went near a hill and got stronger. We'll say those things, but really those only apply to that particular case. And we don't know if that's repeatable. So most of the literature, and Karen and I are as guilty as anyone else, are these case studies, which will get us laughed out of any other science. Nobody studies my favorite electron, right? Or my favorite mouse and says, hey, here's what mice look like. What you have is controlled studies of something. Or you have huge data sets of here's what 1,000 mice look like, and here's the average size or lifespan of a mouse. We've been trying to do that with tornadoes, but mostly we're still doing these case studies. What Karen and I have been trying to do, since we have 250 tornado maps with the DOWs, is look at these tornadoes as a species, as a class of a phenomenon, and say, what's the typical vertical structure? What's the typical evolution? What's the typical size or intensity? But for these better data sets with multiple radars and stuff, we're still stuck in case study land. That was a long answer to us.
Well, it's a tough question. I mean,
we don't know. Yeah.
That's why there's so much about this that is difficult to study for all the reasons that you've described. We have a question about the pods. And since they're so relevant to the work that you're doing, I'm going to pass it on. What is the maximum wind speed the pods are designed to survive, and what are the strongest conditions that you've measured on a pod? Not Greenfield.
So, first of all, you take a look at those pods. Those are not carefully engineered, wind tunnel tested devices. That's a weather station on a heavy piece of steel that we got surplus, and that's it. So how much does it take to tip over a pod? I don't know. We've had some pods damaged. So far, we've never had one tipped over by wind.
No.
We've had them hit by debris. In a tornado, we've had them hit by debris. In a hurricane, we've had them hit by debris. We had one knocked off a bridge, and future archaeologists are going to find it when the sea levels drop again, because it went off into the Gulf of Mexico. But we measured over 100 miles an hour with them. They're pretty close to the ground.
Yes.
Probably 100, 120 miles an hour with the pods. I mean, we've just never gotten one in the core flow of, part of a strong tornado. I mean, 100, 120 at the ground, that's what gets on YouTube as 300 miles an hour, in a selfie, because it looks like it's 300 miles an hour. It's really bad to get those kind of winds. And you can't tell. I mean, unless you really have a gauge there, you can't tell 100, 200 from anything standing in it.
Mesonettes have been 100.
Oh, yeah, our mesonettes have been in 100, sadly. Yeah, twice. We drove into the same tornado twice with a mesonet by mistake, and got over 100, but it was not that strong a tornado. I think we're supposed to be experts here, not doing that, so shouldn't be advertising that.
Reportedly, yeah. A bunch of questions about, focused in two areas. The first is, have you discussed adding airborne technology to collect data, which actually is relevant also to Greenfield and some other data sets this year?
You answer. I can talk. We are using airborne technology. Balloons.
And other stuff too. Yeah. I mean, so that Duke loop that Josh had showed, he showed the Penn State swarm suns, and they're not ours. But that's one of the technologies that we're using. So again, basically like like a balloon you'd normally send up, it has a smaller package. You don't fill the balloons quite the same. And you're trying to be neutrally buoyant. And like I said, hopefully, if you launch it in the right place, get these balloons with instruments measuring temperature, relative humidity, wind into the tornado. So getting information about that. Certainly there's other ways of doing this. People are working on, drone technology and different stuff like that. And there's a big interest really in getting thermodynamic measurements above the surface. That's one of the big things that we're lacking in tornado studies is thermodynamic measurements above the surface. And those are measurements that we think are super important for tornado genesis and tornado evolution processes.
So, yeah, we're trying. It's a challenging but new kind of expanding area of trying to get these measurements above the ground, getting them into tornadoes. The fancier your instruments are, in the sense, the fewer you have and the more you don't want to lose them. So that's tough. So these balloons that we've been trying to get in, we just throw a bunch of cheap balloons out and hopefully they get in. Not unlike either Twister movie where they're sort of trying to get stuff in. So we've been trying that. Yes.
Excellent. Since you began your study of tornado genesis, have you noticed the time from tornado formation and warning to public response has improved at all? Or has there been a shift?
So I haven't noticed that.
I don't.
So, I mean, we've been doing this with Dallas for 30 years now. We don't see the public response most of the time. I mean, most of the time we're out in open fields and there's no public response. Driving through Greenfield, I don't remember. This is totally just from memory, and I wasn't focused on what people were doing. We're focused on, can we get through the town before the tornado hits? I don't remember people out much, so I assume they had responded to a warning already and they weren't driving around or looking at it. So I haven't noticed any change in the public response.
I mean, certainly information is different than it was 20 or 25 years ago. I mean, better radars, people out there reporting more.
Internet.
Yeah.
More.
I mean, a lot more. I mean, so some of that just might be because information's getting out there differently than it was 25 years ago or 20 years ago, when nobody had their cell phone that beeped at them and said, take shelter, you're in a tornado warning, which you get all the time now when you're tornado chasing.
Yep. All right. We're not going to avoid this entirely, so I'm going to dive right in. EF scale. We talk about this a lot, and you touched on it during your presentation. In your opinion, actually, let me back up. Are wind measurements from the DOWs at all being used for damage surveys? If not, do you know why? And given the close range DOW data, like concurrently, given the close range DOW data gathered in Greenfield, would the wind speed measurements help ascertain a more accurate damage indicator, do you think? And you could probably parallel.
I am not a spokesman for the National Weather Service. The National Weather Service made a policy decision a dozen years ago to not use wind measurements, either anemometry, let's say somebody got a pod in a tornado, or radar measurements as part of their EF ratings. So they made that decision. I don't know all of the reasoning of that decision. They have a very systematic and, at least in a statistical sense, kind of stable way of assessing tornado intensity. And I imagine that some of their concern was that introducing actual measurements, either in situ measurements from an anemometer or radar measurements into that occasionally would kind of mess up the statistics. Now, we do know that prior to that decision that the Weather Service did use DOW data, sort of only very occasionally. If they called us up, we told them, hey, we measured 165 miles an hour in that tornado, and they might have only rated it EF1, and they would change their rating. So we know there were several tornadoes over the years that got changed, their ratings, but probably not after 2012-ish was that done. We also know that some of the tornado counts got changed. I mean, for example, after the May 3rd, 1999 outbreak, the Weather Service put out their preliminary maps of where the tornadoes were. And there were two different tracks based on damage surveys. And we showed them that in fact there was a continuous tornado, so they turned 2 tornadoes into one. If Jim Ledoux or those people who are involved with the Greenfield damage surveys are on now, cover your ears, because we are actually going to be doing a comparison of the damage surveys to the radar data, and hopefully independent assessment so we can then compare them for the Greenfield tornado. But I believe that the damage assessment is that there's 1 tornado that went through Greenfield, and we just show you there are in fact 2, and one of them goes just about exactly over the same track as the other one. So when you look post facto at the damage, how could you tell that there were 2 with the same track? But we see it because we see 2 vortices going on simultaneously. So there are differences sometimes there. And again, that's to be expected. There are very different ways of assessing damage. The EF scale is terrific. Hundreds and hundreds of tornadoes, you can do some assessment of intensity. When it goes through towns, most all the time, that's all you've got. It's very rare that the DOWs or any other mobile radar or stationary radar is anywhere near a tornado. I mean, I don't know how many buildings and good EF assessments there were of tornadoes this year, but Karen showed you that plot. We saw 10 tornadoes or something this year out of the 1,000. So we sampled 1%. We're just not there reliably enough to be a repeatable source of intensity information. So the EF scale is absolutely needed.
Personally,
I was going to say one last thing. No, there are major efforts ongoing now. There's a major substantive, robust effort going on now to update how engineers and scientists assess tornado intensity. The EFs, there's going to be a big book published by the American Society of Civil Engineers. The EF scale is going to be one of those chapters, and it's going to have a greatly expanded much more rigorous EF scale. There's going to be a chapter on using radar measurements to assess tornadoes. There's a chapter on how to use anemometry to study tornadoes, how to use satellite data, how to use forensics, tree falls of different sorts. There are all these different chapters that experts then can use to assess tornado intensity. The EF scale is one of those that will probably be the most frequently used, but other methods are going to be well documented with repeatable peer-reviewed standards.
Yeah, I guess I was just going to add on to that since you named all those. I mean, personally, I'm not bothered. I mean, these are different methods of extracting wind speeds. And if people are documenting their methods and, putting this into a database, I mean, we have this then for future studies, if things were to change or if we're getting different information. So I think it's great having different methods because different things happen at different times, and you might have a mobile radar there when there's no damage occurring. And again, as long as people are documenting this and using some, acceptable standard, I think it's going to be great for, future generations and looking back at tornado intensity and what we knew now and what we might know, 10, 20, 30 years from now.
I mean, it's fascinating that we have these very strong wind measurements over 100 feet over Greenfield, while at the damage, the expert teams, and they look really well, noticed on the EF4 damage. Now, there's a couple possible reasons there, which we're going to be studying. One is that the EF meter was essentially peaked. You just peaked the meter in Greenfield because there weren't any strong structures to damage. The second is that maybe the winds were lower than what we measured because of all the blockage, because of the trees and the buildings that were there. It might have reduced the winds at the surface. So one or the other or some combination were factors there. And that is fascinating. It's a fascinating question. And hopefully by comparing these in detail with wind engineers, with expert damage surveyors, we will understand more about what the winds do in that kind of town environment. Because most of our data is over more open country, because that's an easier place to get radar data. We have very few close-up data sets in towns with strong tornadoes occurring.
Also, a third thing, I mean, this was a strong tornado, but these winds last so quickly in some of these tornadoes. And the duration of the wind versus the damage that you see is also something really interesting and something that we're trying to explore more.
Yeah, I mean, very fast tornado, very small tornado. These 300-mile-an-hour winds would have only lasted about a second. Poof, it's over.
Yeah.
As opposed to some larger tornadoes with let's say, and what's worse, would you rather have 30 seconds at 200 miles an hour or 1 second at 300? We don't really know what does the worst damage. A 200 mile an hour wind for 30 seconds has less pressure force on your building, perhaps, but much more grinding effect of debris and things hitting your building and causing damage. And pulses of wind within that 30 seconds. And I can't speak as a skilled wind engineer, but I don't think they really know the subtleties there about which does more damage in the very complex damaging environment of a tornado, of an intense tornado.
Well, and that's part of what makes the Greenfield data set so exceptional, right? Is that it's one of the few data sets we do have at that granular detail in close proximity to a populated area. So that's part of what makes that so exceptional. So I do want to call out, we are now at time. Because of the immense number of questions and participation, we're going to run a little bit over for those of you who are going to hang out with us probably for the next 15 minutes or so. And we are definitely not going to get to all of these questions, so apologies in advance, but I'm looking for repeating questions. And we've got a couple of good ones that I definitely want to make sure we get to before we close out. So, we also have a lot of more technical questions about ADAD, et cetera, that we'll try to get to at the end if we can get to these other two big ones. The first one I want to make sure we talk about is kind of what happens next. So after you gather this data, like let's say just from this season alone, how long will it take you to fully analyze that data? What is your typical kind of process? What are the steps? And then what else are the DOWs up to right now? So are you simultaneously kind of processing the best project while doing other work? Like what's in your near future?
You're still gonna answer after I talk.
I will.
So I'll start with the easy one. Lots of stuff in our queue. So as Josh said, we're getting ready potentially for hurricane season, wildfire season. There's other data sets we're looking at from hurricanes, from the Perils Project, from the BEST project, getting ready for a project next spring, probably. So a lot going on there. In terms of how long it takes to analyze the data, there's lots of ways. I mean, so first of all, there's a lot of quality control and navigation and stuff that we have to go through, see the kind of data that we get, see what, integrated data that we have, and look at that alone, but also look at that in the context of other data sets. And something like Greenfield and some of the other tornadoes, there might be other people that we're working with or collaborating with to look at the data, to look at some certain questions. So I would say, it's sort of a year of, weeding through the data a little bit and doing analyses. Certainly we're going to start presenting preliminary results this fall. But really getting well-formed ideas, well-formed publishable stuff, usually takes a couple of years, if not longer. And certainly if we're looking at it with, a bunch of other data sets and not just doing a case study, that becomes a longer process as well.
Yeah. First, we could call out the AMS Severe Local Storms Conference. If you want to see what we'll call preliminary results that are a few months after the data collection, these are like what we showed today are like super preliminary results. But come to Virginia Beach.
End of October.
Yeah, end of October, the Severe Local Storms Conference. And Karen and I both have talks about BEST and tornadoes and other things too, probably fires and hurricanes, whatever, all the different stuff we're doing. But there are multiple tiers in how we do these analyses. So the first things we're doing, I'll say the easiest, but they're sort of just the fewest instruments. We do have 2 exemplary cases this year, and we probably will do a case study of just Greenfield, just looking at damage versus radar measurements. We're working with Jim Ledoux and some other and some wind engineers to work on that, and those results will be preliminary results will be presented at AMS this fall. We'll probably be doing dual Doppler analysis, those vector analysis we showed you from Duke. That's a more complex, difficult analysis to do. So that might take, again, we'll show some pretty pictures and things and some preliminary results, but the more detailed, careful analysis takes at least a year to do that sort of thing.
Same with thermo.
and integrating the thermodynamic data and trying to make some sense of it. The thermodynamic data, I think, since it's kind of these individual slices in different tornadoes, probably the biggest learning we'll get there is in these more, climatology is probably not the right word for this, but more multi-case, trying to see commonalities. Do we usually see warm air in front of a tornado that's increasing in intensity, or is it cold air, or what's, but trying to look among a dozen or 2 dozen or 3 dozen cases, not just individual case studies. And that's very difficult to do because we don't have controlled experiments and there's a lot of variables that change. So those are the hardest. Karen published a paper, led a paper a couple of years ago looking at these wind profiles where we looked at 73 tornadoes to come up with that 31% curve she showed. But boy, the spaghetti plot there is all over the place. There's a lot of variability tornado to tornado. So what we want to do is increase our database so we can hopefully get a better, statistically better case there. And the same thing with our dual Doppler analyses. Do we most of the time see feature A or most of the time see feature B? So we can get a better, hopefully shorter answer to the question that was asked about tornado genesis. So we're not saying, well, it might be this, or it might be this, or it might be this. The problem is we see all those things in different cases. But what's most common? What's the sort of general statements we can make? So we'll be doing both those things. Some results come out in a few months. Some take a few years to digest.
That's a one.
Got it.
Longer than a few months, probably even for the first results. Yes. Almost as long as my answers.
Exactly. And a lot of times we present results at conferences and stuff, and we get people's feedback, and you sort of think about what people told you and maybe go a different direction or keep going with the direction you're going. So some of it's, vetting it, with the community as well, and seeing.
That's one of the major, so the reason we're going to this AMS conference in October is so we can show preliminary results. We can look at other people's preliminary results and sure, take a look at them, talk, sit over dinner and say, hey, that's really interesting. We've seen that also, or we don't see that ever, or, maybe you're doing that analysis wrong. We basically share our data, share our preliminary results with other scientists so that we come up with a more mature, like you said, vetted answer later.
And then I guess just a quick follow on to that is when you do have results come out, where can people find that kind of stuff?
Well, usually AMS has recorded talks. So the preliminary results usually come out in these AMS recorded talks. We also try usually to give public seminars and talk about some of that as well. But ultimately we publish in, usually AMS journals or AGU journals, just peer-reviewed journals by a professional society.
Yeah, so they're in the technical literature. So most of these kind of results, let's say we do a dual Doppler study of that Duke tornado. Maybe that shows up in an AMS journal or an AGU journal. Some of these that climatology we were showing was in PNAS, Proceedings of the National Academy of Sciences. If we have a, groundbreaking, I guess some things we think are groundbreaking, the world doesn't think are as groundbreaking as we do, but we'll publish them in some more general science journals. So we've had papers in Science in the past, but it sort of varies. But usually it's in the technical literature. Now, sometimes we'll have some overview type papers in BAMS, the bulletin of the AMS, which are less technical, more approachable. But again, it varies. These kind of results probably are mostly in the more technical journals. So Monthly Weather Review, Weather and Forecasting, those type AMS journals. And some of your participants here are probably very familiar with those journals. Others, if they haven't had a lot of meteorology experience or math experience, they might be harder reads.
We keep a list of our publications. So we have a website and all our publications are there. We also have, PDFs so people could download that and take a look at anything that we've published in these technical journals.
Maybe we need to have a follow-up. Maybe we need a follow-up webinar in 6 or 8 months. All right. And I want to close with the last question. We've gotten this repeatedly, and it centers around getting involved. So if folks would like to, for example, are there opportunities for students to work with the team on projects like internships or research projects? Is there a way to get involved? How can people engage?
Yeah. Well, so it varies a lot. And so we get a lot of emails all the time where people want to come out and chase with us. And that's fine. And sometimes, and we do, when we go out for one of these projects, we sometimes, a lot of people, Vortex 2 was the one, we keep saying that, and that was a while ago, but that was huge. We had 150 people out with Vortex 2. So there were lots of students of various ages and education levels out there doing these projects.
We had a lot of perils.
Out in Perils, which was a tornado project in the Southeast a year ago, that Karen was leading. 110 total. A lot were different universities were there. So, NOAA was out there, but yeah, Texas Tech, Penn State, Illinois, OU, North Carolina State University. So there were students out from all these different universities getting involved. So it's not just our team, but it's teams we work with. We're doing a big hail project this coming spring. So we'll have a team out that's mostly our small group. We just have 7 people. But the universities that we're working with and are using the DOWs and other systems will have, 50 people out.
Yeah.
Now, most of those are students of those universities, but they'll probably be looking for other people to participate on any given day. In terms of analyzing the data and working on those projects, usually it's students who are at the universities who are doing the research. So we've had, for example, this Perils project we talked about. There's different students at the University of Illinois, at the University of Oklahoma, Texas Tech, North Carolina, Penn State, who are working on that data as either senior projects or their master's theses or their doctoral dissertations, just at various levels, working on that data.
So I will say, in terms of field project and participants, I know people, if that's probably sometimes the more fun stuff. Really being flexible. I mean, a lot of times people are, not flexible in when they can come out, or can only come out for a week or something like that. If you want to do sort of serious participation in these projects, usually people who are pretty flexible with coming out and have, those it usually works out better for both us and for the people that are participating. And hurricanes.
And I was about to say hurricanes. And for this fall, do you like to drive a big truck? Would you like to go to the coast in some rain and wind? No. When we do hurricane missions, we're very short of people, and we are very hard pressed to get our trucks from here in Boulder, Colorado, to the coast. Let's say Florida or Alabama, wherever we're trying to go. And so we are always scrambling, trying to get people. But what we really need are drivers because we're in a very short time frame at the last minute, trying to get our trucks to the coast. So if you are interested in truck driving, these kind of, they don't see the screen. That kind of truck that's right behind us to the coast, and you see a tropical storm coming or developing or about to hit the coast, send us an email.
Yep, got it. So I'm hearing.
And by the way, this is how Karen joined our program. She came out for some tornado work, but then she came out
and never left.
And never left. She actually, we have a lot of people come out for one hurricane and it's so miserable they don't do it again. But Karen has been in a lot of hurricanes now. It was fun.
It was great fun.
Yeah, absolutely. So I'm hearing if somebody wants to get involved, they should contact you all via the email, probably on the farm website. What is the farm website? I'm going to catch you guys.
It's something horrible. Google it. Just look farm, DOWs, University of Illinois.
Yeah. And I will add to that, because there was a great question from Katie with AMS. For sure, it helps to have weather-related skill sets. So there's some useful overlap, and folks who have experience in storm chasing and can recognize different parts of the storm and contribute from that perspective. Truck driving, I'm hearing, if you're a student, there were several universities listed that might be looking for assistance in that route. So you've got some options.
Well, for example, for hail, so there's a big hail project happening next spring. And what are the big universities?
Northern Illinois, Penn State, CU, Central Michigan University, University of us, but we don't have students.
Yeah.
I was just trying to think. Those are kind of the big ones. Purdue.
Yeah, several universities there we listed. There's probably some others. But if you're at those universities, ask your professors. If you're not, they still may be looking for people to participate in the spring because there's a lot of students needed and they may find themselves, we think they might find themselves needing some extra students.
I mean, I think we need like 50.
Yeah, but it's different every spring, and it's different universities every spring. The big obvious universities that are out, Penn State, OU, Illinois, Colorado State, Florida State, those universities, North Carolina State, those universities do have opportunities every so often for doing field work, but not necessarily every single year, every project. I mean, it kind of comes and goes.
Yep. Awesome. All right. I know we've run over well and good now, so I'm going to hand it back to Gideon to close us out here on behalf of AMS. So thanks.